Hi, in this course I teach the basic graph theory and algorithms. If you are new to this channel, please consider subscribing. Today in the third lecture we will discuss about simple graphs and regular graphs and all, and two simple theorems also. So firstly we will go through the definition of simple graph. So any graph without any loop or any multiple edge is called simple graph. Okay, so there should not be any loop or any multiple edge. For example, we have drawn this figure. This is a graph, and here there are only two vertices u and v, and there is only one edge. So this graph is a simple graph because there is no loop or no multiple edge also. So it will be easier to consider a counter example for better understanding. So let us consider this graph. Okay. It is also a graph on two vertices, okay, but it is not a simple graph because there is a loop. Okay, so the difference between this graph and this graph is basically the presence of this loop. Since in this graph there is a loop, so it is not a simple graph, and since in this graph there is no loop and no multiple edge, this is a simple graph. Also we can consider another example, say this one. So here there is no loop, but there is a multiple edge between u and v, so it is also not simple graph. So these two examples are basically counter examples. Okay, so these are actually counter examples. Okay, so now we can consider another examples. For example, let us take this graph on 4 vertices. There is also, we can see that there is no multiple edge, no loop, so it is also a simple graph. Okay, and we can consider one more graph. Let us take this one. Okay, so this is also a simple graph because here also there is no multiple edge, no loop. Okay, so these are examples. So now we will consider this proposition which states that in any simple graph the maximum possible degree is n minus 1. So we will quickly prove this proposition. So in case of simple graph there is no multiple edge and no loop, and already we know that degree of a graph is the number of edges incident on a vertex. So we will write down this, that degree of any vertex is number of edges incident on that vertex. Okay, so since there is no loop in simple graph, there is no loop and no multiple edge. So the only edge is simple edge, that is between any two vertex there can be at most one edge. There can be no edge also, but if there exists some edge, then the number of edges can be maximum 1. Okay, so for any vertex v in G, it can be adjacent if let the number of vertices in G be n. Okay, so the cardinality of the vertex set of G is n we are taking. Then for any vertex v, except this v, there are n minus 1 other vertices. Okay, so we are denoting these other vertices by red color and say these are other vertices. So number of these other vertices is n minus 1. Okay, so then v can be adjacent with this n minus 1 vertices at most. It can be adjacent to less than n minus 1 vertices. Okay, so it may happen that v is adjacent to none of them also, but if it is adjacent to them, then v can be adjacent with at most n minus 1 number of vertices. Okay, and then there can be at most n minus 1 edges incident on V, because there is no loop and also there is no multiple edge. So V cannot be adjacent with this vertex say U by 2 edges. It cannot happen, since this graph is a simple graph. So there can be at most n minus 1 edges incident on V. Okay, so we have to write down that. So V can be adjacent to at most n minus 1 vertices, and so number of edges incident on V can be at most n minus 1. So the maximum degree will be at most n minus 1 from here. So the maximum degree is less than or equal to n minus 1. So here the proof is complete. Okay, so now we will prove this theorem. This theorem states basically that in any simple graph, if it has n number of vertices, then there exist at least 2 vertices with same degree. Okay, and to prove this theorem, we will use a principle called Pigeonhole principle. So firstly we will write down the statement of that principle, and then we will start the proof. Okay, so this Pigeonhole principle basically states that if there is m number of nests and n number of pigeons, okay, and this number n is greater than or equal to m, so this n is strictly greater than m, that is number of pigeons is strictly greater than number of nests or holes we can consider, then there exists at least one hole or one nest which contains more than one pigeon, that is at least 2 pigeons. Okay, so like that, if there are say m number of nests and n number of pigeon, when this n is greater than m and this n number of pigeons, then if we now start to put that pigeons into these nests, then after filling this m number of nests, if we consider that the pigeons are like first pigeon is going to here, the second pigeon is going to here, and so on, then filling all these nests, since this number n is greater than m, so there exists at least one pigeon which is extra. So this, if that pigeon we put into any of them, then at least one hole will contain more than one, that is at least 2 pigeon. Okay, so this is basically the statement of that principle. Now we will use this principle to prove this theorem. So we will start the proof here. So basically now we will see the possible degrees of the vertices. So firstly, G has n number of vertices. Okay, and we have already seen the possible degrees of the vertices. Okay, so the possible degrees are what? From 0 to n minus 1 for each vertex. Okay, so possible degree is 0, 1 to n minus 1. Now we have to consider 2 cases. Okay, so firstly we will consider case 1. If there exists a 0 degree vertex, if G has a 0 degree vertex, that means that this vertex is isolated vertex. Okay, so this vertex V, it has degree 0 and we are considering that degree of V is 0, then it is adjacent to none of them. So it is adjacent to none of the n minus 1 other vertices. Okay, so we are considering this to be G prime. that is the induced subgraph. We will discuss later what is induced subgraph, but let us consider now that V is a vertex, and except itself there are n minus 1 other vertex, and this V is not adjacent to any of them. Okay, so now this graph is except V, this graph G is of order n minus 1, and so any vertex here will have degree at most n minus 2. Okay, since we have already seen in the previous proposition that any vertex with n number of vertices has degree at most n minus 1. So for this case here, any vertex except this V, which this V has degree 0, and except this V, any vertex here has degree at most n minus 2. Okay, it is the maximum degree. So then what will be the degree, the possible degrees for this graph? The possible degrees will be 0, 1, 2 up to n minus 2. Okay, not n minus 1, because if there exists say any vertex with degree n minus 1, then it has to be adjacent to all the n minus 1 other vertices, but this V is not adjacent to this vertex. Okay, so for this reason here the possible degrees are this. So we are writing down this, that here the possible degrees are given by this 0 to n minus 2. So there are total n minus 1 numbers, and there are total n vertices. Okay, so there are n vertices and n minus 1 possible degrees. Okay, so if we consider now these vertices to be pigeons, these to be pigeons, and these possible degrees to be holes, then we can observe from the Pigeonhole principle that there is at least one hole which contains two pigeons, which contains at least two pigeons. So using that we can now state that there exists at least one possible degree which is attained by two vertices. Okay, so there is at least two vertices in the same hole, that is with the same degree, Okay, so now we have to consider another case, which is that if it is not there, if G has no 0 degree vertex. Okay, so case 2 states that there is G has no 0 degree vertex, that is no isolated vertex. Okay, so then the possible degrees are what? The possible degree cannot be 0. Okay, so the possible degrees are, in that case the possible degrees are 1, 2, 2 up to n minus 1. Okay, so here also the same case, the number of possible degrees, there are n minus 1 choices and number of vertices is n. So in that case also similarly we can write that similarly there are n minus 1 n number of vertices and n minus 1 possible degrees. Okay, so there is at least two vertices with, so there is at least two vertices with same degree. So here this proof is complete. So now we will prove another proposition, that in any simple graph maximum number of edge is at most n into n minus 1 by 2 when cardinality of the vertex set, that is number of vertices, n. Okay, so to prove this we will use this proposition, that is in any simple graph maximum possible degree of any vertex or of the graph is n minus 1. Okay, so this is simple graph, then the maximum, we from that proposition we have that maximum degree of any vertex of G is how much? It is n minus 1. Okay, and number of vertex in G is n. So maximum degree of the whole graph G is n into n minus 1. So by handshaking theorem we have that from handshaking theorem what we have, that handshaking theorem gives that 2 into E is equal to total degree of the graph. Okay, so it is equal to the total degree of the graph. So now we have that the total degree is less than or equal to n into n minus 1. So what we have, that 2 into E, which is equal to the total degree of that graph, total degree of G is less than or equal to n into n minus 1, which implies that E is less than or equal to n into n minus 1 by 2. So which is our desired result, that any simple graph has the maximum number of edge n into n minus 1 by 2. So here this proof is complete. Now in the next class we will discuss about regular graphs, and we will discuss some more theorems on this topic. So please consider subscribing my channel, and please like and comment for more videos on graph theory. Thank you.